I'm really excited to be part of the first live deployment of galaxies. And I think we had a great first talk by Pedro about how galaxies work, and he also showed this picture. I'm going to be talking a little bit more about this specific picture and how it's made and how we sort of learn about galaxies in general from it. And also focusing specifically on the most distant galaxies. I want to disappoint you all, or prepare you all for some disappointment. I'll show you the most distant galaxies in this pretty good picture. If you're in the back, you probably don't see it. If you're in the front, you probably don't either. These are really interesting scientifically. I'm going to show you that. But I think my mother is still a bit disappointed that I don't send her really pretty pictures. So this is actually our galaxy. So we heard a lot about that in the last one. If you're lucky enough to be somewhere that's very dark at night, and where there aren't a lot of clouds, so presumably very far away from here, this would be the view that you see, okay? And so everything in this picture, basically anything you see with your eyes when you're outside at night, is a star or something else in our galaxy, okay? And we've learned a lot about our galaxy in many of the ways that we just looked, right? So we learned that our sun is one of about 200 billion stars in this galaxy. We think it has this disc shape and a spiral structure, and we think that in this direction, right, towards past all of these gas clouds and dust, we think in the very center there's a supermassive black hole, right? And I think maybe it's part of human nature to want to think or believe that our galaxy must be special somehow. It must be really cool and really interesting. And I'm telling you that that's actually not true. Our galaxy is really average in all of the properties that I mentioned, right? So in terms of the size of the galaxy, the fact that it has a black hole, the fact that it's shaped like this with a spiral structure, right? These are very normal properties of galaxies. And the reason we know that is because we spend a lot of time looking for other galaxies, right? This is not trivially easy. Like I said, anything you see with your eyes is something inside our galaxy. So we've had to spend a lot of time looking outside of our own galaxies. So it's a bad idea in general. If you're looking at a telescope, you don't want to look through the center. There's a lot of stuff in the way. So we spent a lot of time basically looking at nothing, right? Looking in directions away from things that we can identify to go and potentially give us the best chance of finding things very far away. Now I showed this picture very intentionally. So this is the Hubble Space Telescope over there on Earth. And this has really, since the early 1990s, been the best instrument that we've been using to go and find other galaxies. So it was originally launched, I think, in the early 1990s, and you may know there was a problem actually. So after it was launched, it was not able to take very clear pictures. Some astronauts actually had to go, what they say is they gave it a pair of glasses to fix the optics, and then it was able to take clear pictures. So one of the first things that people wanted to do with Hubble was actually a potentially very brave and very bold thing. They wanted to spend a lot of time looking very, very deep, making a very deep picture of the universe, right? Because telescopes are sort of like light buckets, is what we say. So you basically collect the light, and if something is very faint because it's very far away, you need to be collecting the light for a very long time in order to be able to see it. Okay? And so these brave people in 1995 spent 10 days looking at a single point in the sky, trying to see the most distant things that they could. Okay? Hubble is not very good at taking big areas in terms of photographs, right? It's not a wide-angle instrument. So it looked at an area of the sky that is this big compared to the full moon, so really, really small, right? That big, and they spent 10 days doing it. Okay? I think this is really incredible. And they didn't know what they were going to find. They found one of the most empty regions of the sky, where they really didn't think there was anything, or potentially nothing. And what they saw was incredible, actually. So this is actually, I think, the name certainly does not give it justice. Astronomers are very bad at naming things. We call this the Hubble Deep Field. Right? But in contrast to what you see with your eyes, in this picture, almost everything is a distant galaxy. Right? And this one picture alone, in this very tiny area, there are more than 3,000 galaxies. And I think that really took the entire community by surprise. I don't think anyone expected there would be this many galaxies in such a small area. Now, scientists, of course, maybe it's possible that they randomly picked a very interesting area. So they repeated the experiment. They repeated the bad name. They put this in the southern hemisphere called the Hubble Deep Field South. But the same picture of the picture. Basically, anywhere you look in the night sky, outside of our galaxy, anywhere that's sufficiently dark, you see thousands of other galaxies, right? Each one of these has millions or billions of stars. Many of them are a lot like our Milky Way. Now, since the 1990s, we've upgraded Hubble. We've given it new cameras that are more sensitive. Cameras can, for example, look in the infrared. And so this is the crowning achievement of those kinds of studies, Hubble Ultra Deep Field. But this is essentially the deepest picture we've ever taken of the universe. The faintest, the most distant sources that we've ever been able to see are all contained in this image. And I want to walk you through a little bit on a few interesting galaxies here so you get an impression of the sort of detail that we actually have from this. So I'm going to highlight this galaxy first, and I've changed the color a little bit from here into here. This is a galaxy that's actually a lot like our Milky Way, but it's actually much further away. So it has about the same size, the same number of stars as our Milky Way, the same spiral structure. You can also see that towards the center it's a bit more red, on the outside it's a bit more blue. So we think at the center of the galaxy there's more dust, which makes things look a little bit more red. We also think that the stars there are older. On the outside you have younger stars being formed, so it's a little bit more blue. Right? But this is how we know, looking at galaxies like this is how we know that our Milky Way is pretty average. Now, there are some cases like this one as well. There's actually two galaxies running into each other. It's what we call a galaxy merger. Right? So we have two of these spiral galaxies. And we think over the course of the next few million years, they're going to merge and combine into a completely new galaxy. Right? So gravity is pulling them together and turning them into one. And we think that eventually they're going to look something like this. Right? So this is a completely different type of galaxy. So it's not a spiral galaxy, it's what we call an elliptical galaxy. So it doesn't have that disk shape, it's more round, with the highest number of stars in the center, and then the number of stars decreases further out. And I think this one is pretty cute, because once you move far enough outside on this particular galaxy, you can actually start to see that there's something behind it. Right? There's another galaxy even behind this one. And that's the point of pictures like this, is that there's actually an incredible amount of depth in this two-dimensional projection of the image. Now, I mentioned at the beginning I was going to talk about the most distant galaxies. I told you to be prepared for a little bit of disappointment. This is the most distant galaxy. Right? No one can see it, right? And I kind of withheld a little bit of information. So this is actually what you would see in visible light, right? So light that our eyes are capable of seeing. But I also mentioned that recently Hubble had cameras installed that can look in the infrared. So actually, you can only see something in the infrared, right? It's just this tiny little dot, right? But this is entirely what we expect to see from the most distant galaxies in the universe. And I want to tell you why we think that's the case. In order to do that, I need to give you a quick physics lesson. Right? I promise there won't be any equations. Certainly not going to be any chalkboards. But I want to talk a little bit about light. And you actually heard this, I think, from some of the quiz and the introduction things. Right? So light is a wave, and light, for example, from our sun, can be dispersed into the full spectrum of the rainbow. Right? And so our eyes actually just identify these different wavelengths of light as different colors. So as you can see here, for example, red light and orange light are the longest wavelengths that we're capable of seeing. Blue and purple are the shortest wavelengths. And so stars like our sun emit most of their light and most of their energy in these colors, which is why evolution has made our eyes sensitive to those. But there are wavelengths that are longer than red, which is called infrared, which you may know if you have a thermal camera, or wavelengths that are shorter than this, which is what we call ultraviolet, and we know that's what gives us sunburn, for example. Now, it's not necessarily very intuitive to think of light as a wave. I think people have a much easier time understanding waves when it comes to sound. And there's actually a very interesting physical effect with sound that I'm sure you're all familiar with. It's also very important for galaxies. That's called the Doppler Effect. Okay? So this happens when a source is emitting sound. So say you have a fire truck and it has a siren going off. If it's standing still, it's going to sound the same no matter where you are. But if it's moving very quickly, if it's moving towards you, you hear it as a higher pitch. If it's moving away from you, you hear a lower pitch. So basically what happens, as you can see in the cartoon, the sound waves, when it's coming towards you, they get compressed. And the shorter wavelengths is what we hear as a higher pitch. When it's moving away from you, they get stretched out. We hear that as a lower pitch. And so actually the same thing happens with light. You have to be traveling much, much faster than a fire truck in order for this to happen. But if, for example, the light bulb is moving very quickly towards you, we would then perceive it as being bluer and say it's blue shifted. If it's moving very quickly away from you, it would become red, and it's red shifted. And this is really, really important when it comes to astronomy, because the universe is actually expanding. So in the early 20th century, people like Hubble and Maseda discovered the universe is expanding because there was a Big Bang. The universe started with a Big Bang, there was a huge explosion, so everything started moving away from each other. Now you can imagine this, if you had a bunch of things on the surface of a balloon. As the balloon expands, every point on the surface is moving away from every other point. Right? So if you're a galaxy, let's say, on the surface of this balloon, you view every other galaxy as moving away from you. And actually what's happening is sort of the space in between you and the other galaxies is expanding. So the further something away is from you, the faster it's moving away. So there's actually a relationship between that speed and then the amount that it actually, the distance that it is away from you. And so if we can measure the redshift for a galaxy, we know how far away it is. Right? And so what we actually do with something like Hubble is we don't take a color picture like you do with your camera. We have lots of filters and we take pictures of individual colors. And then we put them together into one color image like this. So you'd expect, for example, if this particular galaxy was redshifted, you'd expect the purple light to become blue, the blue to become green, green to become yellow, and so on. And if it's really, really redshifted, you basically only end up seeing the light that's sort of blue or ultraviolet, but you'd only see it then at infrared wavelengths. You wouldn't see anything in the visible spectrum of what we would expect to see. And of course, if this were very far away, it would also be very, very small. And that's different than something that's just very close but very small. Right? So in the case of something that's very small, you'd still expect to see the same ratios, so for example, green light to yellow light to blue light. Okay? So it's pretty easy to tell those apart. So then we think that the most distant galaxies that we would actually be able to see would only have their light visible in the infrared. And so that's the case of a galaxy like this. This is one of about 5 or 6 in that particular image, amongst the most distant galaxies that we've ever been able to observe. And because light takes a finite amount of time to travel anywhere, we're actually looking at this galaxy. We're looking at the light that was emitted from this galaxy when the universe was basically 4% of its current age, right? So more than 13 billion years ago. So using this sort of method, by looking at these distant galaxies, we're taking pictures of the universe when it was really, really young. And if we can study these galaxies in a lot more detail, we can learn more about what sort of processes were important in galaxies in the early universe. I think hopefully in the next few months we're going to have a lot of talks that are more specific about the processes that go on in those galaxies. But I want to give you all a last impression of how hard this actually is, why we need something like Hubble, and why we need to spend so much time doing it. Right? The brightness of this galaxy is a 100-watt light bulb 10 million kilometers away. Right? And the size, this angular size, would be this screen 4,000 kilometers away. Right? Incredibly small and incredibly faint. And so we're starting to assemble samples, like I said, a few tens of these types of galaxies. We're hoping in the next few years, with new telescopes, for example, like the James Webb Space Telescope, we're going to start to get much larger samples of these and really develop a much better picture of how galaxies were like in the early universe. So I end by showing you a little movie. So as I mentioned, that ultra-deep field is really a two-dimensional projection of a three-dimensional space. And so this is just sort of a fly-through, showing you the distances of all of these galaxies in this direction, so you can also see the spatial relationships. So I want to thank you all for your attention and be happy to take any questions.